Imagine digging for treasure, right? And finding it in just the most, well, impossible place. What if I told you scientists just uncovered this colossal, mysterious reservoir of fresh water? Not under some desert, but deep beneath the ocean floor. It's one of those discoveries that genuinely makes you, rethink what you thought you knew about our own planet. So today we're doing a deep dive into this very story. It comes from a fascinating article in SciTech Daily titled, "Scientists Discover Mysterious Freshwater Reservoir Beneath the Ocean Floor. How did it get there?"
Mhm.
Our mission here is to really unpack this incredible find, get into the extraordinary challenges the scientists faced getting to it, and explore why this isn't just like a hidden pool of water. It's potentially something much bigger for understanding Earth.
Exactly. What's truly captivating, I think, is the sheer audacity of this discovery. It really forces us to question some fundamental ideas about Earth's geology, its hydrology. I mean, this isn't just another scientific paper. It feels more like a key chapter in this ongoing detective story about our planet, revealing secrets we didn't even know were there to be found.
And what a secret. The core finding is, well, it's genuinely astonishing. They found an unusually large body of what they're calling freshened water, far offshore New England, specifically near Nantucket. And this wasn't some lucky fluke, was it? It came out of a really ambitious expedition, led by Professor Rebecca Robinson from the University of Rhode Island's Graduate School of Oceanography.
Right, and that's precisely where the mystery deepens quite significantly.
Yeah.
Because normally when you drill into sediments under the seafloor, you expect salt water. Salinity levels pretty much matching the ocean right above it. Salt water all the way down, basically. So finding a substantial body of fresh water miles under the seabed, that just fundamentally challenges the standard picture of marine geology. It really makes you ask, how on earth did it get there? And maybe even more puzzling, how did it stay fresh for, well, who knows how long?
That is truly baffling. You said
That quote really hits the nail on the head. Water that's close to drinking water limits. I mean, that suggests an incredible amount of isolation from the salty ocean above and around it. It means this water hasn't significantly mixed with seawater for a very, very long time, which points towards some really effective trapping mechanisms, maybe layers of impermeable rock or sediment acting like a kind of geological seal, a cap. It definitely implies a historical process, something maybe related to past sea levels being lower or perhaps glacial meltwater infiltrating these formations way back when. They got sealed off as the oceans rose or sediments piled on top. It's almost like finding a pristine time capsule buried deep underground.
a time capsule.
Yeah, that's a great way to put it. So obviously, this incredible find has just kicked off a whole new wave of questions, a whole new investigation. Scientists are now grappling with these really fundamental questions, almost like the first clues in this planetary detective story, as you said. How exactly did this water get trapped down there? How long has it been hidden, preserved like this? And crucially, how much water are we talking about? What volume does this massive underground reservoir actually hold? The implications could be huge. And getting answers, well, that wasn't exactly a walk in the park. It took this major effort they called the New England Shelf Hydrogeology Expedition, a truly collaborative and ambitious undertaking. 41 researchers from different nations, different scientific fields, all converging, spending 74 demanding days out at sea. That sounds like an incredibly intense couple of months.
Oh, absolutely. Intense is the word. And you're right, the human element in these long expeditions is vital, often kind of overlooked. What always strikes me is the sheer grit required. The resilience. Just imagine you're cooped up on a 185-foot vessel for over 2 months. You've got the unpredictable ocean, the constant noise of machinery, and this immense pressure to get this unique data. It's a massive test of endurance, sure, but also teamwork, complex problem solving, not just as individuals, but as a whole group working together. That camaraderie that builds under pressure, it's incredible and totally essential for tackling the technical hurdles that inevitably pop up.
And those technical hurdles sound pretty formidable. The scale of the operation alone, staggering. They used that 185-foot lift boat you mentioned, fitted with a compact drilling rig. And with that, they recovered an amazing 718 cores from the subsea floor. That adds up to over 871 meters in length. That's nearly a kilometer of Earth samples.
Right.
And maybe even more impressive, they managed to extract 50,000 liters of this groundwater from various depths. Just to give you a sense of that, 50,000 liters, that's enough to fill maybe, 1,000 standard bathtubs? It's a lot of water to pull from so deep.
It is. And getting that volume of water, plus all those sediment cores, from deep beneath the seabed was far from simple. Rebecca Robinson herself pointed out how tough it was. She said, "It was a challenge to pump significant amounts of groundwater out of the wells without destabilizing them." Think about it. You're drilling into what's often soft, unconsolidated sediment, miles below the surface, under huge pressure. It's kind of like trying to carefully suck water out of a wet sandcastle without the whole thing just collapsing inwards. So to stop that sediment column from caving in and ruining their samples, they had to be incredibly strategic. Their whole approach involved meticulously figuring out where to pump from, precisely controlling the flow rate, carefully positioning all their equipment. These were all variables they were learning to optimize, basically on the fly. It was a real triumph of both engineering skill and geological know-how.
That kind of precision sounds incredibly difficult. You wonder if there are any moments where it almost went wrong, where success really hung by a thread, maybe they nearly lost a core or destabilized a well. It feels like they were operating right at the edge of what's technically possible.
Oh, I'm sure there were. Well, the article doesn't detail specific close calls. Anyone who's been involved in that kind of deep-sea drilling knows those moments are just part of the process. The constant adjustments, the fine-tuning under immense pressure, the long hours just monitoring sensitive equipment. It's all about trying to anticipate potential failures and reacting instantly when something starts to go sideways. The fact that Robinson was, as you quoted, thrilled with our success in sampling such difficult formations and with the astonishing amount of water we were able to recover for science, that really tells you just how challenging it was, how close to the edge they were probably operating, and what a massive achievement it was to succeed so well.
Right, so they pulled off this incredible feat just to get the samples. Amazing. But the real deep dive into understanding what it all means, that starts now, back in the lab, right? What are they hoping to figure out from all this precious water and sediment they brought back?
Exactly. Finding the water was maybe step one. Now the real detective work shifts to the laboratory. One of Rebecca Robinson's main research goals, for instance, is to study the nitrogen in this groundwater, its origins, its history. Why nitrogen? Well, all organisms need nitrogen to live. So how nitrogen cycles within that water acts almost like a chemical fingerprint. It can reveal different types of microbial processing that have happened over time. Learning what happened to the nitrogen along its flow path underground can tell them something about the water's journey, what environments it passed through, what it interacted with, maybe even indicating ancient life forms that were consuming or altering the nitrogen deep down long ago.
Ah, okay, so they're not just looking at the water HO, but all the dissolved clues within it to paint this really detailed picture of its past life, so to speak. And to do this, Robinson's team will be using something called an isotope ratio mass spectrometer. For those of us, like me, who aren't in the lab every day, how does that kind of tool actually help unlock the story hidden in the nitrogen?
Right? It sounds complex, but think of it like a super advanced chemical detective kit. That's a good way to put it. It can measure really subtle variations in the atoms themselves, different versions or isotopes of nitrogen. These tiny differences in atomic weight act like specific signatures. So, for example, finding certain nitrogen isotopes might tell them if the water flowed through zones rich in ancient decomposed plant matter, or maybe if it interacted with specific types of bacteria living deep underground without oxygen. It basically helps them piece together the environmental conditions, maybe even the biological activity, that this water encountered during its long, hidden journey beneath the seafloor.
A chemical detective kit. I like that analogy. It makes sense. And connecting this to the bigger picture, the nitrogen study is just one piece of the puzzle, isn't it? I think you mentioned other researchers will be focused on actually dating this water, finding out how old it is.
Precisely.
Yeah.
And this is where it gets really, really exciting from a historical perspective. Other scientists on the team, yes, they'll be measuring the age of the water using what are called radiogenic isotopes, things like carbon-14, maybe helium-4. These isotopes are essentially natural clocks that are embedded within the water molecules or dissolved gases. By measuring how much they've decayed over time because they degrade and known, scientists can calculate how long that water has been isolated from the atmosphere. This dating provides absolutely critical clues about things like past sea levels, major glacial melt events from ice ages, and the specific geological twists and turns that trap this fresh water way down there. I mean, if this water turns out to be, let's say, tens of thousands of years old from the last ice age, that's a mind-blowing insight. It could completely reshape how we understand ancient climate shifts and how Earth's water cycles operated millennia ago. It's like having a direct sample of the planet's past.
Wow. That sounds like it needs a truly global scientific brain trust. Not just for the science itself, but managing all the different parts. It's really fantastic to see that level of collaboration. The article mentioned that besides Professor Robinson, the other chief scientists were Professor Brandon Dugan from the Colorado School of Mines and Professor Karen Johannesson from UMass Boston. Just all these brilliant minds working together on this. And the work isn't finished by a long shot. The immediate next steps involve a big meeting, right? The research team is going to convene at the University of Bremen's core repository over in Germany. That's planned for January and February 2026. What's the significance of physically bringing all those samples together in one place like Bremen for this next phase?
Oh, it's absolutely crucial. Bringing all those hundreds of core samples to a dedicated, state-of-the-art repository like Bremen, it allows the entire international team and eventually the wider scientific community to meticulously examine them under ideal lab conditions. Things they couldn't necessarily do on a moving ship.
Yeah.
They'll collect even more detailed data, run additional tests, and then collaboratively start writing up their preliminary reports, comparing notes directly with the physical evidence in front of them. This kind of communal examination really fosters a more holistic understanding. It ensures multiple experts, multiple perspectives are looking at the same evidence, validating findings, cross-referencing everything. It's really where the initial pieces of this complex puzzle start to properly fit together.
And that commitment to collaboration, it extends beyond just the initial team, too, which seems like a great model for how science should work today. The article notes that after a one-year moratorium giving the main team first crack at analysis, these precious cores will be archived and made accessible for more research globally.
Yes, it does. And this open access approach is really pivotal for modern scientific discovery, especially in bigger science projects. All the expedition data eventually will be open access. Every resulting paper will be published. This makes sure that the incredible insights gained from this massive effort aren't just locked away within one group, but can actually benefit countless other scientists around the world. It really fosters a truly global scientific community, helping to accelerate discovery by allowing everyone to build on this shared foundational knowledge. It's all about collective progress, really.
And we should definitely give a nod to the crucial funding support that makes these kinds of groundbreaking, expensive expeditions even possible. This particular project got backing from IODP, that's the International Ocean Discovery Program. Specifically, its European Consortium for Ocean Research Drilling, or ECORD, and also, of course, the National Science Foundation here in the U.S. Without that kind of major institutional support, these grand scientific quests just wouldn't get off the ground. So as we kind of wrap up this deep dive, we've journeyed, metaphorically speaking, beneath the waves to uncover this hidden world of freshwater. It's a discovery that really does challenge our basic assumptions about where Earth stores its most vital resource. It reminds us that even in places we think we know, like the ocean floor off New England, our planet still holds some incredible secrets.
Absolutely. This whole exploration into subsea floor freshwater, it really underscores just how much more there is to learn right here on our own world. It's not just about finding a potential new water source, although that's interesting in itself. It's more about understanding the incredibly complex dynamic history of Earth's water cycles, its ancient climates, how geological processes have literally shaped our planet over vast stretches of time. It really proves that sometimes the greatest discoveries might still be lurking right beneath our feet, or, well, in this case, way beneath the seabed.
So as you listening think about this vast, unexpected freshwater reservoir, just imagine what other hidden resources, what other geological secrets might still be lying undiscovered beneath the world's oceans. How might finding such a significant, previously unknown water supply change our understanding of, say, resource management in the future? Or maybe shed light on past climate changes we haven't fully grasped yet? What other potentially drinking quality surprises might our planet be holding on to, just waiting for curious minds like the ones on this expedition to uncover them?